Okay, great. All right. So today we are starting our string theory course. I have to say that, well, we could also call it, we could also have started and calling it a quantum gravity course, but we already had a quantum gravity course, so we had to come out with a different name. So this could be part 2, if you wish. So let's start a little bit from the beginning and say, well, what do we have, or what have we learned in the 20th century? So we have learned that we have general relativity. Okay, that's a very nice and successful theory. And probably this will be the 100th time that you have seen the action, but I'll write it nevertheless. Perhaps the reason is that this is the first and last time that I'll write it with 16 pi, g, and all that. So I figured it would be nice to do it at least once. Okay. And we also have the standard model of particle physics, which seems to be spectacularly successful, much more than what we wanted, really, in the sense that even at the LHC, everything is working spectacularly well. Perhaps we might be even very, very close to finally pinning down the Higgs. Then everything will be spectacular here. But what is a standard model? The standard model is a quantum field theory that lives in flat space-time. Okay? So what we're learning here is that quantum field theories are a very, very good description of nature. Okay? So how do we describe it? Well, the standard model is a quantum field theory, so it has an action. And it has tons of things like this. Where this F square stands for, I guess you know what, the curvature of the gauge field, right? The field strength is the F, okay? So the standard model is a gauge theory, first of all, and it contains many factors like this. But what I want to stress is that it's a quantum field theory in flat space-time. Now, the two actions look very similar. You would say, well, they are just actions. And we know that in quantum field theory, we just quantize this, use a path integral, and we're done, right? Then we get all these spectacular predictions. How about in general relativity? Well, you could try the same thing. So that would be step 1. You could say, well, we cannot have two actions and treat them completely differently, okay? Pretend that this is just a theory that we can use it at the classical level, and this is a theory that we have to use it completely in the quantum to give a nice description of quantum theory. So we have to do something with general relativity. The step 1 would be just to try and use it as a quantum field theory in flat space-time, okay? That's the first thing you should try. Any responsible person would sit down and look at this and say, well, let's just give it a shot. Okay, so how would you do that? So the step 1 is to give it a shot at treating general relativity as a quantum field theory. Okay, so how do you do that? Well, the first step is to expand that of flat space-time. So you take the metric to be the Minkowski metric plus a fluctuation. Well, let me call it MR. Okay? Where this MR is what is called the reduced Planck mass. Okay? It's roughly 10 to the 18 GeV. The usual Planck mass doesn't have the 8 pi. And that's why you probably have seen in books or everywhere that this is 10 to the 19 GeV. Okay? Okay, so once you do this, you treat this as your fluctuations, as your quantum field. And you want to know whether this thing makes sense as a quantum field theory. So now your action is a functional of your field H, and you want to expand it. And when you do, you have to expand everything, even the square root of minus g. Of course, I'm not going to do that. I'm just going to say that here you get the free Lagrangian, okay, for your gauge field, plus first term is something like this. And the first surprise, you might be disappointed with that, is that you get an infinite number of interaction vertices. Okay? So this looks like a very, very complicated quantum field theory. But nevertheless, you can still give it a shot, okay? And see whether it makes sense. So the first surprise is the following. You do a one-loop computation. What do you think you find? There are two options. One, that the theory is divergent, okay, UV divergent, which would be bad, right? And the other one is that the theory is not divergent. What do you think? Not divergent? Yes, divergent. Who thinks it's going to be divergent? Raise your hand. Only 3. Okay. Maybe I should have asked, who thinks it's not going to be divergent? Wow, there is more. Yeah, so, okay. Very good. Well, it turns out that pure gravity is what is called one-loop finite. So indeed, it's not divergent. Well, there is a simple reason to understand why that's the case. If it was divergent, there should be some counter term we should put into the action in order to get rid of that divergence or to compensate for that divergence. But then you can check that the possible counter terms that you can put that will contribute to a one-loop computation would be things that can be reabsorbed by field redefinitions, except for just one term. Okay? But that particular term is something that is called a topological term. Okay? Have you seen topological terms already in your GR courses, like Gauss-Bonnet terms in 4 dimensions? No? Yes? So there is a... Okay. So maybe you have seen it, but not in your courses. That would be a consistent story with the... If some people say yes and some people say no. Okay. Well, these are terms that you can construct from the curvature, okay, such that when you integrate them over space-time, they give you just a number that has to do with the topology of the space-time that you're dealing with, okay, with the topology of the manifold. So at one loop, everything is finite for pure gravity. Then you get excited. You say, okay, this is it. We're going to get nature in one shot, just adding this thing with that thing, and then we're going to be done. But before getting too excited, let's go and check 2 loops. Okay? Then you do a 2-loop computation. Gorov and Sagnotti did it. They worked very, very hard, and they found, what do you think? Was it finite or divergent?
Divergent.
Divergence. Who says finite? Nobody? Okay. Well, they found a divergence. Okay. So they found a divergence, and they found that this divergence could be canceled if you add to the action, to that action, something that looks like 1 over epsilon, 1 over m Planck, I think, to the 4th, d for x, square root of minus g, r mu nu, rho sigma, r rho sigma, gamma delta, r gamma delta, mu nu. Okay? Well, that would be the contour term. And epsilon, do you know what epsilon is? This is all done in dimensional regularization. Okay? So it's just a dimensional regularization parameter. There is a divergence. There is a contour term. It's not topological. That's why the divergence happens there in perturbation theory. So that's the end of the story. Pure gravity is not a finite theory, or it's not even renormalizable, because you have to add this term. Of course, we know that the theory had a dimension-full parameter, so really the only chance that we had was that the theory would be finite. Okay? Well, but there is something else. And that something else is that you can ask, well, let's go back to the one-loop computation and add the standard model, or just add any matter that you like. Okay? So this was a disappointment, but perhaps something nice will happen if you add some matter. Say you add the standard model. Okay? Add the standard model to your one-loop computation and see what happens. Okay? So what do you think happens?
They're very happy.
You're not in a very positive mood. But, well, it's true.
Okay, good.
So you add the standard model, and your nice one-loop computation is gone. It also diverges. So the moral of the story is that even if you're building your theory of quantum gravity and things seem to be working nice, you have to keep in mind that the moment you try to couple to the standard model, which is of course necessary, otherwise you're not doing anything, then life can get more complicated. And everything that you have done can be destroyed in 1 second. Okay? So that's very, very important. Whenever you're dealing with a theory of quantum gravity, you should keep in mind that you have to incorporate matter. Otherwise, you're not doing anything really that will have any chance of describing nature. Okay. Very good. So it seems that we cannot do a quantum field theory of general relativity or Einstein gravity. But before panicking, we should say, or we should try to use the power of analogy, right? And say, has this ever happened before in physics, or something similar to that? Then we look back and learn that something like that was happening. There was a very successful theory that didn't make sense as a quantum field theory. Okay? So probably you have heard about that. That's Fermi's 4-fermion theory. For the weak interactions. Okay? Well, what happened there? Well, Fermi had a very nice Lagrangian that described many of the phenomena that were happening in the weak interactions, but the theory was not renormalizable. What's the solution to this problem? What was the solution? Well, the theory had to be interpreted as a theory that was valid up to some cutoff. Okay? So that's what we now call effective field theories. But, well, that's basically the technical word for the solution of the problem. This was an effective theory. What does it mean that this is an effective theory? That there will be another theory that will replace it. Okay? And what was the replacement? Right. The standard model itself. Okay? So what it was discovered was that we also had, we also had to add W's and Z bosons, and then our 4-fermion interaction was replaced by a nice interaction where we had W plus minuses propagating there, okay? And this came from a theory that could be made renormalizable. So we could ask the same thing about gravity. Could it be that general relativity is just an effective action of something else? So the question is, could GR be an effective theory of another quantum field theory? Okay? But before we do that, or before we try to answer that question, we could ask, is there any chance, or is there any theory? Well, in fact, if it's a quantum field theory, we have to be a quantum field theory that somehow contains gravity. So the question is, another question we could try to address before doing that is there any quantum field theory of gravity? Never mind that it has a standard model, just any quantum field theory. We don't care what is the matter content, anything that will have as a propagating degree of freedom a massless spin-2 particle. Okay? Well, the first thing we can do is to go back here and say, well, what we want to do is to mix this Lagrangian with some Lagrangian with matter fields in such a way that these divergences will start to cancel. Okay? Is that possible? Well, remember that divergences came in loop diagrams, okay, when our gravitons were propagating in the loop. Now, you all know, I hope, that if you have a fermion propagating in a loop, you usually get something different from the case when you have a boson propagating in a loop. What's the difference? There is a minus sign, right? So if you were able to cook up an interaction so that this minus sign will help you cancel the divergence of this plus sign, then you will be in business, perhaps. Okay? So this is something that you probably saw today in Beyond the Standard Model. I'm not sure if you did. But one motivation to go beyond the Standard Model is that the mass of the Higgs is very unstable, right? It has this nasty top divergence, right? The top running in a loop is contributing to the mass of the Higgs. Did you see that today? No? You'll see it tomorrow, I'm sure. Definitely. Now, in order to cancel that, okay, what you have to do is to add another particle that will precisely contribute with a different sign. So the top is what? A fermion or a boson? Is what? Well, this was maybe it was an anion or something like that. So, who thinks it's a boson? A fermion? Okay, good. So what you need is a boson, right? So in the Standard Model, we have our Higgs, and we have this top loop. So you need something else to cancel that. And if this is the top, you need a boson that runs there that is called the S-top. Okay? So you probably have heard that there is a big deal nowadays going on, perhaps rumors about maybe an S-top. But there might be some S-top signs somewhere. So here we can do the same thing. Okay? We can try the same thing. Okay. Well, let's give it a shot and see what happens. So we need something that is a symmetry. Clearly, the fermion we want to put here has to be related to the boson that is running here. Otherwise, the divergences will not cancel. So there has to be some sort of symmetry that exchanges bosons and fermions. Okay? And of course, You know what this symmetry is called, because it's very famous. It's called supersymmetry. Okay? Well, what do we do with supersymmetry? Well, if we have massless particles, here is where it's going to get interesting, because I'm going to start asking questions about the Lie algebra and Lie group course that we saw at the beginning. So if you have a massless particle in 4 dimensions, what classifies them? How they transform under the little group. What is a little group in 4 dimensions? Yes. And what is the number that we can use to classify our massless particles? It's called helicity. Do you remember? So we classify our massless particles by their helicity. Okay? So what's the helicity of the star of the show today, which is the graviton? So the graviton has helicity, what? Could be plus or minus 2, right? Gauge bosons, the regular gauge fields, have helicity plus minus 1, but gravitons have helicity plus minus 2. So we describe our particles by a state, or our asymptotic particles by states of helicity minus 2 or helicity plus 2. Okay? Now, this new symmetry, this supersymmetry acting on massless particles can be represented as an operator that we're going to call Q, and its Hermitian conjugate, Q bar, say. And what they do is that they act on a state. Well, Q acts on a state of some helicity and raises the helicity by a half. Q bar lowers the helicity by a half. Okay? So if we apply that operator to our minus spin, to our helicity minus 2 state here, what do we get? So we're going to get a state with helicity. I told you this guy raises the helicity by a half. So this state will have helicity our state here will have helicity 3/2, minus 3/2. Okay? Now we can apply Q bar here on this state. And get something that has helicity plus 3/2. Now, why do I have to worry about these guys? These guys look perfectly fine. Remember, minus helicity particles and plus helicity particles don't talk to each other. Why don't I construct a theory that only has negative helicity particles?
CPT.
CPT. We believe that CPT is a symmetry of nature, and CPT exchanges those guys with the other two guys. Okay? Or this guy with that guy. So we cannot build a theory with just one kind of helicity because it will not be CPT invariant. Okay. So if we have this object here, we also have to include these ones here. Okay? Now, this particle combined is what is called a gravitino, which we will probably talk about in beyond the standard model. Okay? So we have the graviton together with the plus helicity there. We have our graviton, and we have a gravitino, which is a funny object. It has a vector index, and it also has a spinor index. Okay? Very good. So now we got this guy, and this guy definitely cancels the divergence at one loop. Okay? It's a way of adding matter so that we don't spoil the cancellation that we saw at one loop. In fact, we make it even more explicit. So what happens at two loops? What do you think? Okay. Okay. Does everybody agree with, what? I forget, what's your name?
Andrew.
Andrew, yes. Does everybody agree with Andrew? No divergence or divergence? Well, this is a theory. The theory is n equals 1 supergravity. I'll tell you why it's called n equals 1, but just a theory of a gravitino and a graviton. So what do you think? I already told you there is one loop finite. What happens at 2 loops? You were right. It's finite. Okay. Very good. Now, there is something else that is interesting. If you're given, somebody tells you that there is in nature something called the gravitino that has helicity minus 3/2 and 3/2. Okay? And they tell you to couple to gravity. It turns out that there is only one consistent way of doing it. Even if you didn't know about supersymmetry, if somebody just told you that this thing had to be nature, and you are asked to write down a Lagrangian that contains both, there is only one way to do it. And it turns out to be supersymmetric. That's kind of interesting. It says that, well, if this guy is really nature, we're bound to see at least a supersymmetric sector somewhere. And that would be in this sector. Okay? Yes?
Why do you consider graviton and gravitino are like different fields? They are not excitation of the same.
Oh, very good question. Yes. So I could try to write a superfield. Okay? And these would be components of that superfield. Right? So that would be better indeed. Yes. But one reason not to do it is that there is no superfield formalism for what we're going to do next. Yes.
Is there any intuitive way to see why actual loops is finite, like some non-renormalization theorem?
Yeah, there is a nice way to see why. Yes. The reason is that this guy, as an interaction in the S matrix, will give you an S matrix element. It will tell you that if you scatter particles with helicity plus and plus, well, here I'm using the convention when everybody's incoming, right? When you compute S matrices, the natural thing to do is everybody's incoming. So if you have plus 2, plus 2, plus 2, and minus 2, this object gives you a non-zero contribution for this S matrix element. But there is a Ward identity, a supersymmetric Ward identity, that tells you that this amplitude has to be 0. It's very easy to show. So that already kills. It says that any supersymmetric theory, this term cannot possibly be there. Or in other words, it tells you that this term cannot be supersymmetrized. So it cannot be there in the supersymmetric theory. Yeah, there was, yes.
What happens if we add a standard model? Is it still fine?
I told you we were not adding the standard. Yeah, we said we don't care. Yeah. If you add the supersymmetric version of the standard model, you get that divergence again. Yes. But I said that we were not going to worry about the standard model. We said we would just try to find any quantum field theory of gravity. Any. I mean, that would be spectacular. It doesn't matter that it's not the same. I mean, if we find one, that would be incredible, right? Okay, very good. Now the next, of course, the natural question is what happens at 3 loops? Please.
They're very thin.
Okay. Yes, it diverges.
I think
Okay.
I'm just putting the fun.
No, you're making it more surprising.
Question.
Yes.
Are there some intuitive reason to see that, like for example, here at two loop level it's finite, and at 3 loop level it's divergent?
Well, at 2 loops, I already told you how to see it. At 3 loops, the way to do it is just to write down a counter term, and you realize that it's possible to write a counter term which is consistent with one supersymmetry. you can write a nice contour term.
You have to do the calculation.
Yeah, sorry. Yeah. That's life sometimes, yes. Okay.
Question?
Then you say, well, yeah.
I didn't really understand. Does Susie say that we have to add the gravitino? Or why did we add those Q?
Sorry, what's the question again?
Did supersymmetry say we had to have the gravitino? Why did we have the Q?
Well, supersymmetry is precisely, is a symmetry that is generated by these objects, right? And their action on the Hilbert space is to do this. Oh, I forgot to say one. Okay. So what they do is precisely to map this bosonic state into a fermionic state, okay? So that's why it exchanges bosons and fermions. Is that the question? So you had to produce a fermionic state. If you started with the bosonic state, you have to produce a fermionic state. Okay? Very good. Now, I also forgot to say that these Qs anti-commute, okay? So you cannot apply it again. But then we say, well, things are working fine, right? I mean, we added one supersymmetry, and we made it finite. The 2-loop was finite. Now the 3-loop diverges. So that's an improvement, I would say, right? Well, if a trick works once, why not do it twice, right? We cannot apply the same Q twice because that would be 0. But who tells us that there should be only one kind of supersymmetry? Maybe there could be 2 kinds of supersymmetry. Okay? So maybe we can have 2 kinds of generators. Let's call them Q1, Q2, and their corresponding bars. Okay? So the previous one, we're going to call it n equals 1 Susie, or n equals 1 Sugra. That's what it's called, n equals 1 supergravity. Okay? Now we're going to do n equals 2 supergravity because it has 2 supersymmetries. So what is the theory? Well, the theory is obtained by saying we start with our graviton here. We apply Q. Let's call it Qi, right? Because it could be any of these 2. And we produce 2 possible kinds of gravitinos. Okay? But now we can apply again another Q. Of course, once we apply the next Q, there is only one possibility, because we cannot repeat the index because they anti-commute with each other. So we will get 0. So this is the only possibility acting on -2. And this thing has helicity what? Well, if we have helicity -1, so this will be a state with helicity -1. This one was our state with -3/2. And these states are gauge bosons. Okay? And there is only one of them, right? Because there is only one possibility. Plus their CPT friends. Okay? The other ones we have to add. So once again, I told you there are 2 loops. The argument that the theory, any supersymmetric theory was finite was very simple. So this is finite. And the question again, for Andrew perhaps, is what happens at 3 loops? Well, anyone. What do you think? Any guesses? Is it finite or it diverges? Finite. What do you think?
I think it doesn't go finite. But now I don't want to
No, you don't have a
say anything.
solution.
No, you have to make now. You have to make a statement.
Diverges.
Diverges.
Yes.
Okay. Let's see, what are the chances that you got right all this? In other words, there is no symmetry that protects the appearance of this three-loop counterterm. Okay? So you would think, and everybody thought that perhaps the theory was dead. I mean, that's it. I mean, there is no improvement. We're not doing any better. So we're not doing any better, but nevertheless, we can still hope that something else will happen if we increase the supersymmetry. Now, how much we can increase supersymmetry? So what is the maximal amount of supersymmetry? Well, if we start with our state with helicity -2, and we apply a QI, we get the gravitinous. Now we get the gauge bosons. How many Qs can we have so that at the end of the day, the maximal amount will be such that when we get here, when we get to that maximal number, we will get something that has helicity +2. And that would be a unique state, okay? So that would be the maximal amount of supersymmetry we can have. Because if we had more, then we could keep going, and we would produce things with higher helicity. So what is the n
8.
that does the job? 8. Very good. So n equals 8 supergravity is a theory with maximal. Yes?
What's the problem with going to higher helicity?
Very good. First of all, well, there are several problems. One of them is that if we go higher, of course, if we have something here of, say, helicity 5/2, by CPT, we will also have to add the other one, right? So the theory would be a bigger theory. And it is believed that there is no consistent way of writing down a Lagrangian for a massless particle with helicity greater than 2. Okay? All right. So this will be the maximal theory, the maximal supergravity. One reason I mention in this theory here is that it will appear again. In a string theory, this theory will somehow show up. In fact, as a low-energy effective theory. Okay? So this will be an example of a low-energy effective theory of a theory of quantum gravity. So that would be interesting. But still, we can take this theory and do our little table again. At one loop, of course, is finite. At two loops, is also finite because this was true for any supersymmetric theory. How about three loops? Any ideas? You say finite. What do you say? Diverges. Well, that's what everybody thought. It diverges. Everybody thought that it diverges because the three-loop counterterm can be made n equals 8 supersymmetric. It was fine. We can make it supersymmetric. We can write it down. Therefore, it could be there. But it turns out that a few years ago, around 5 years ago, Bern et al. Did a heroic 4-particle 3-loop computation in n equals 8 supergravity. And guess what? They found that it was finite. Well, the natural thing to do, of course, is to try 4-loop computation, which they finished in 2009. And I'm not going to ask this time, because I already got Andrew. That's all I wanted to do, really. Turns out to be finite. Oh boy, for loop, finite. They haven't finished the 5-loop computation yet. They are working on that. It's probably this year. This year they will tell us what happens at 5 loops. But now everybody's expecting that at 5 loops it's going to be finite. Yes.
It doesn't go like.
No, well, to test the appearance of the counter term, all you have to do is a 4-particle computation to test the appearance of the counter term that could be there. So they have shown that it could not be there at 3 loops and at 4 loops. Yes.
Didn't you show that any quantum field theory for gravity would be unrenormalizable?
Yes. Yeah. I mean, that's what we think we know. But this is 4 loops. There is still an infinite number of loops to go.
Right, but if all of them are finite, then
well, of course, if they are all finite, not only is renormalizable, it's finite.
Yeah.
And that's even better, right? It's much better than being just renormalizable. Renormalizable is for losers. Being finite is really something.
Would it not be nicer just to check what happens at the n loop and then put for n whatever you want?
Well, well, this is just to show you that there is something. I mean, yeah. If you ask me why did they do this computation when everybody thought that it was divergent, I really have no idea. Well, no. I know. I know. Because they were seeing already at one loop. At one loop, they were seeing already things that were not supposed to be happening. Gravity was behaving. N equals A supergravity at one loop was doing things that were much more special than anything that you would expect from purely supersymmetry. So they thought, well, if at one loop, N equals A supergravity is doing all these nice things, maybe there is something going on. So why don't you give it a shot and do a 3-loop computation and spend like 2 years of your life doing a 3-loop computation? Well, but in the end, it was very good because they destroyed the thing that was in the mind of everybody. Everybody thought that it was divergent. Now it's known to be finite. At 4 loops, it's also finite. Now the question to answer your question is like, well, of course, we cannot keep doing this, right? Because it would be incredibly impossible now to do, say, a 10-loop computation, right? But there must be some reason why this is happening. If the theory is going to be finite, there must be some symmetry or something or something must be responsible for this, for being finite at those loops. It turns out that this theory, has a symmetry, has a global symmetry. Which is called E77. So the symmetry was known to be there for a long time, but it was thought to be anomalous. So it was thought that the symmetry will not help you at loop level because it will be broken by quantum corrections. Now it's understood that it's not anomalous, so it must be there. Any quantum correction must respect this symmetry. I'm hoping somebody will ask, well, what? We saw E7, but what does it mean E77? What is the 7 that is next to it, right? Well, E7 is a group is an algebra that has 133 generators, as you remember from last time. Now, as a complex Lie algebra, okay, there is only one Lie algebra, but as a complex Lie algebra, you can choose several different real sections. Okay, you can choose some of the generators, and you can make some of the generators to be purely real or purely imaginary. And depending on what you choose, some directions will be compact and some directions will be non-compact. That's the difference between SL2R and SU2. They both come from the same complex algebra. But remember, when you choose the generators to be purely real, you get a nice SU2, nice compact object, which is S3. And if you choose them to be purely imaginary, then you get something that is non-compact, which is SL2R. Okay? So you can always make a choice and say that the number of generators splits itself into the number of non-compact generators plus the number of compact generators. And the number that people usually write here, in this case is 7, is the difference between the two. Okay? So in this case, it means that N is 70 and C is 63. What does this mean? Well, that E7 has a compact, or this E77 has a compact subalgebra, which is SU8 in it, and it has 70 non-compact generators. And what are these 70 non-compact generators? Well, here is a nice exercise for you. Look at the scalars here. Helicity 0. Okay? The guys with helicity 0, apply as many Qs as you need to go to helicity 0 and count how many there are. How many different states you can generate. And the number you can generate is 70. That is this 70. Now it's understood that the 3-loop counterterm that was consistent with supersymmetry is not consistent with E77. The 4-loop counterterm is not consistent with E77. The first counterterm that is not consistent with E77, or sorry, that is consistent with E77 is a 7-loop counterterm. So our friends will have to do a 7-loop computation, or somebody else will have to come out with something better to actually check if that counterterm is there or not. Okay?
So isn't it better to go for 8 loops already to see whether the correct is or not?
Yeah. Why? See, if you're going to 7, why not 8? One, yes. Right. Very good. Very good. Okay. I just wanted to give you an overview of what we know today. Okay, this is as of today, and probably this year the 5-loop computation will be finished. So that was a serious comment. Okay. Still, the general belief now is that the theory will be finite up to 7 loops, and then it will diverge at 7 loops. So we're not going to be yes.
But does supergravity have other bad things that we don't like? Because we only look at it as a low dimension, low energy limit. It's only for these divergences, or also it has some other bad things?
You mean whether if the theory has?
I mean, why? Because supergravity was abandoned for a long time after it was discovered.
Well, it was abandoned the moment the first person showed that the 3-loop counterterm could be made supersymmetric. The theory was abandoned as a fundamental theory. It could be an effective theory, and indeed it is, as I said. But
if it's an effective theory, why do you care about these divergences?
Oh, why do we care now about these divergences? Well, it still would be very interesting conceptually to find a purely field theory that is a consistent theory, right? Of course, we know that in the end it would still give us trouble because there are non-perturbative states like black holes, right? That the theory will not be able to describe nicely, and we know that a string theory does. So, and a string theory has as the low energy effective action this theory. So, this theory we know already that it needs some other states that it doesn't have in order to be consistent. But still, it conceptually would be very, very interesting. Okay, so now let's move on. I just wanted to give you a snapshot of where we are now. But I hope I've convinced you that if you're looking for a theory of quantum gravity, at the very least, it has to do 2 things. One is at low energies, it has to give you GR, okay? It has to give you a space-time, a macroscopic space-time. And you cannot imagine how hard this is in many of the approaches of quantum gravity. So this is a major requirement, okay? And something else is that we need the standard model or something that will reduce to the standard model at low energies. And we still need our theory to be consistent. Okay? So imagine that we said, well, okay, we give up quantum field theory. So quantum field theory will not give us the answer. So our step 3 in searching for a quantum theory of gravity would be to say, well, now I panic. There is nothing I can do with what I know. So I have to change a paradigm. Somehow, I have to change something. I have to make something dramatic in order to change the situation. Okay? But whatever thing we do, we have to check the spectrum and find our helicity plus minus 2 states. Okay? Otherwise, we're not even talking about gravity. Okay? So every time you do something crazy, you have to check that you're going to produce these states. Otherwise, you're not talking about gravity. The other thing is that when you turn on interactions, the theory should remain consistent, remain mathematically consistent. Okay? And last but not least, we need, if we call this A and B, you need A and B to be satisfied. Okay? Now the big question is, well, we're here to talk about string theory. This is not good. So I told you, we're in the mood now of changing a paradigm. So we're back to string theory. What was the big, deep, new idea that led to string theory? Right? I told you, now we are in step 3. We have to change a paradigm. We have to do something revolutionary. We have to do something new, big, deep. Well, the answer to this question is nothing. Really nothing. The reason is that the theory was discovered by accident. As many good discoveries in science, it was discovered by accident. Okay? It's not that people were faced with that problem with the step 3 and said, well, we have to change a paradigm. Let's try to invent something that will give us a theory of quantum gravity. In fact, the origin of string theory was different. It was not that search for a big and deep new idea, but it was just discovered by accident. Okay? And that's what I want to show you in the next 5 minutes. Let's see. We can use this. So what were people trying to do when they stumbled upon string theory? So we have to go back to the 60s in order to answer that question. And what was the situation in the 60s? In the 60s, we had strongly interacting particles. Okay. So these strongly interacting particles, in particular, there were mesons, some mesons, being discovered almost every day. So there will be news every day. A new meson was discovered. It has this mass. It has this spin. Remember now, we're talking about massive particles in 4 dimensions. What is the little group? SO3. So the representations are classified by what? By the spin. Okay. So people would discover new particles all the time. They saw it, that they saw them as resonances, and then there would be news about new particle at this mass and this spin, new particle, this mass, and this spin. Well, when you're giving all that data, what's the natural thing to do? Well, you start to make plots and see if there is anything interesting going on. Well, they discovered that the mass squared of the particles being discovered, right, or being found, was proportional to the spin of the particle. So the constant of proportionality is called alpha prime. The reason is that really the relation was something like alpha of m squared, say, as a function of m, and then the slope is alpha prime. Okay, you just take the derivative. Right. Okay, so people were finding this, and this was very interesting. But finding all these massive particles was actually a big headache. Okay? One reason is the following. Let's consider the scattering of some of these particles. Let's consider a scattering of 4 particles, 2 going to 2. Okay? So we have 2 particles. It doesn't matter who they are. These are some particles that will interact with all these massive particles that were being found. Okay? So say you have particles 1 and 2, 3 and 4, and these would be the new particles that you're finding, which have some mass. Okay? They have some mass related to the spin like this, and they have some spin j. Okay? Now, how can we write down what this Feynman diagram give us, roughly speaking? Okay? Let's call S P1 plus P2 squared, and T, let's call P2 plus P3 squared, and U is the remaining Mandelstam variable. Okay? So P are the momenta of the particles. So let's try to write this down. What would be the contribution here? Let's assume that the particles that you're scattering here have a spin 0. Okay? So it's a spin 0, and this has spin j, and this has spin 0. Okay? So how can we find that out? Well, something that we can do let's look here from the Lagrangian. If we have particles with a spin 1, what is the cubic interaction? Well, the cubic interaction here, remember the cubic interaction is something of the form, so if you have the spin 1, the cubic interaction there was something of the form a squared del a. Right? When you span f squared, you get something like this. Do you remember when we did the spin 2, the cubic interaction, was it like this or different than this? Can you check in your notes? I didn't want to erase it, but I did. It was h del h squared. If you remember from your notes, that's what we got. So this means that in the cubic interaction, we have 1 power of the momenta. And in this case, it means that in the cubic interaction, we have 2 powers of momenta. Okay? You can show that the same thing will be true if you increase the spin. So for a spin j, you will have j powers of momenta. So that will be at these vertices. Okay? Now, if you do the contractions, you will find a power in the numerator, which should have 2 times j powers of momenta, and it will be something of the form t to the j, where t is this. So it's 2 powers of momenta to the j, divided by the pole in this channel. And the pole in this channel will be s minus mj squared. Okay? So that would be the contribution of this Feynman diagram. Very good. mj here is the mass of the particle propagating, right? This is the propagator. This is just a 3-level diagram. The only new thing is that you might not have seen is what happens when you have particles with high spin, and their contractions will give you something like this. Okay? Now, this looks good. Okay, what's the problem with this? Well, one problem is the following. If you have your 4-particle interaction that depends on ST and U, now imagine that these external spin 0 particles transform in the fundamental or transform in the adjoint of some Lie algebra, which could be isospin or something. Okay? So on SU2 perhaps. Then you can decompose this as a color factor. Sorry, it's not color factor, it's a gauge group or it's not a gauge group either. It's a symmetry factor, an algebra factor. Let's call it CST times a piece or only Feynman diagrams that have poles in the S and T channel, another symmetry factor, let's call it TU, that has, and here US. Okay? So these are just different, the thing is that people usually call this color, but in this case it's not color. So I should come out with a different name. These are different Lie algebra structures here. So you can think that here there is a Lie algebra structure constant FABC, and here there is another one. And these things can contract in different ways. So you can expand your amplitude and collect pieces with different structures in front of them. Okay? And now what is known from quantum field theory is that there is something known as crossing symmetry. Have you seen this in quantum field theory? You probably saw that in quantum field theory, one can show that there is crossing symmetry in the S matrices, which in terms of this, it means that this must be equal to this. Okay? Or the amplitude in the S channel can be related to the amplitude in the T channel by analytic continuation. Okay? Now, from knowing this, let's see what happens to the amplitude in the S channel, or what the amplitude looks like in the S channel. In other words, I'm going to write down only the Feynman diagrams that contribute to the S channel. The T channel is a channel where we have 1 and 3 coming together and then producing 2 and 4. Okay? So what do we get? We get an infinite sum. It's a sum that runs from J of this Tj over S minus Mj. Okay? That's what we get in the S channel. Now, in the T channel, we get a sum over S to the j, T minus M squared j. Okay? Well, this is very common in field theory. In field theory, we get one contribution in the S channel and one contribution in the T channel. And in order to satisfy crossing symmetry, all we do in quantum field theory is to add up the two terms. Okay? Here, we could do the same thing. We can declare that the total amplitude is the sum of these two terms. Okay? Well, that looks a little bit funny. I mean, two infinite sums, that's not very satisfying. So we're going to end the lecture today by mentioning something that was perhaps a big, big piece of inspiration, which is the following. Well, now, let me mention something first, a problem at loop level. Suppose that that was a picture, really. So at loop level, what do? Imagine that we now have a loop correction to this diagram. So we have our particle here, our scalar particle goes here, goes there, here, 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 and we have our spin j guys coming here. So what would be, if we have a loop momentum L running here, what would be the behavior of this diagram? So we'll have to compute it, but we're only interested in the UV behavior. We want to see how bad this thing behaves, okay? So we want to know what happens for a large momentum. Well, we have these two propagators, right? So we have 1 over L squared, one from here and one from here, okay? We don't care very much about anything else. We care only about the behavior for large momenta. And now we have these guys, which are the ones that we have over there. So we have something that looks like L squared to the j divided by L squared, okay? We're neglecting masses and all that because we're considering the behavior of this integral when the momenta is very, very large, okay? So what do we get? We get two such factors, one from here and one from here. So this integral behaves like L to the, so that would be, let's put a square here. So it would behave like L to the 2j minus 4, I believe, right? So for j equals 0, this is completely fine, okay? It's not divergent. For j equals 1, what do we get? Well, for j equals 1, we get something that looks like dl4 over L4, which is like L cubed dl over L to the 4th, which is dl over L, which is a logarithmic divergence, which is something we know how to deal with. But starting for j greater or equal than 2, we get terrible divergences, okay? So we're going to be in trouble here. Okay? So here comes the big inspiration. Coming from Veneziano, he found a way of solving the two problems in one shot by introducing something called the dual hypothesis. And the dual hypothesis is that this object in the S channel has to be equal to the same object to the T channel of the same amplitude. exactly as I defined it there. How is that possible? That looks very, very strange, right? One formula has poles in T, and the other formula has poles in S. How can this even make sense, right? This is seems to be a stupid thing. Well, but do you know any infinite series in one variable, right, that actually has a pole in that variable? Well, imagine you have this series, right? Is it silly to think that this guy can have a pole in X? It's not silly. It actually has a pole in X, right? Because this thing is 1 over 1 minus X. So indeed, this thing, infinite series, can develop poles in the variable that we have there. So somehow this requirement tells you that every pole in the T in T that this guy has to be reproduced by this infinite series. Okay? Well, given just that data, go and find a function that does that. Right? Well, it sounds impossible. In fact, yeah, it looks very, very, very surprising that such a thing exists. But it does. And Veneziano wrote it down. Where alpha is alpha prime times the variable plus some constant, and gamma is a gamma function, which is the integral from 0 to infinity of dt over t, e to the minus t, t to the z. Okay? So here is a nice exercise for you. Show that this object does what it's supposed to do, okay? Never mind what the masses, well, from here, you see you don't have a freedom for what the masses are. You have to compute them to see whatever comes out of here will be the masses that will appear there. So in a sense, there is nothing tunable here except for alpha prime and alpha 0, only two parameters, okay? So exercise shows that this is true. Okay. Now, the only thing that you really need in order to do this exercise, you don't even need to know what this function looks like as an integral. All you need to know is that this function satisfies this identity. Okay? Of course, you all know that this function is related to the factorial, right? In particular, gamma of 1 is equal to 1. But note that gamma of 1 equals to 1 means something interesting. It means, so let's do it here, and then we finish. It means that if you write gamma of z using this formula as gamma of z plus 1 divided by z, it tells you that gamma of 0 has a pole, right? Because as you approach z equals to 0, this thing is equal to 1, and there is a pole here. So gamma of z has a pole at z equal to 0, with residue 1, okay? Not only at z equal to 0, but now you can see that if you keep doing that, right, you can show that it has poles at every negative integer value. So by using that and using this formula, you should be able to recover these two things. Something interesting can happen sometimes when this and this develop poles, but that's why Veneziano introduced this thing here. That would be an unphysical double pole. But Veneziano introduced this gamma in the denominator in order to precisely cancel the double poles that could arise from these two formulas. So probably he started out with this times this, And he realized that this formula will have double poles, and that's why he introduced this term in the denominator. Okay? So I think we can stop here and continue tomorrow towards string theory.